When you run an at-risk simulation, at-risk allows you to filter either inputs or outputs in several ways. Probably the most frequently used filter is to filter out extreme values in one or both tails of a distribution, but this is only one of many possibilities. You can create filters from the Define Filters button on the at-risk ribbon, or you can do it with the Filter button on several at-risk report windows. I will illustrate the possibilities on the model of discounted cash flows shown here. This model was adapted from one of the at-risk example files. The uncertain inputs appear in green font, and the single at-risk output, NPV, appears in maroon font. The Define Filters button lets you restrict input or output values by conditions you impose. As you can see, this button is disabled until you run a simulation. So the first step is to run the simulation. The distribution of NPV without any filters is shown here. It will be useful to keep this graph in mind as filters are added. For example, around 250,000 for the 95th percentile. Then you will see the effects of the filters. The Define Filters button provides several options, two of which are illustrated here. First, you can apply a filter to an input. I will do it here. There are three options. It's either off, standard, or iteration. I will use iteration. I will make the percentiles the 25th and the 75th. And I will apply this filter. This filter restricts the annual revenue growth rate to be between its 25th and 75th percentiles. Remember that the simulation has already been run, so some of the iterations had growth rates beyond these limits. However, when you click Apply and then browse the NPV result, you will see results only from the iterations that satisfy the filter conditions. In other words, you will see the output distribution only for the restricted range of this input. However, to get this behavior, you have to select iteration as the type. Here is the filter distribution of NPV. It turns out that the annual revenue growth rate has a large effect on NPV. So by restricting the values of this input to a narrower range, the NPV is also restricted to a much narrower range. For example, the 95th percentile was originally about 250,000. Now it is only slightly above 100,000. If you change the type of filter for this input from iteration to standard, the effect is less interesting. Now only the graph of the input is affected, as you see here. The graph of the NPV output reverts back to its original form. The second use of the Define Filters button is to apply a filter to an output. This can be used in conjunction with or instead of a filter on an input. Here I will use the latter option. So the first step is to clear the filter on the input. Now I will create a filter on the output, NPV. Its type can be either standard or iteration. They both have the same effect. And I will restrict it to be between the 10th and the 90th percentile. Now I will browse NPV. And I see only a restricted range of values, the middle 80% of the NPVs. An alternative way to apply the same types of filters is through the Filter button at the bottom of several at-risk results windows. For example, to apply a filter to an input, you can select the input cell, click Browse Results, Click the filter button, and you get the same options as before. You can also apply a filter to an output cell in exactly the same way. To clear any or all filters, you can click the Define Filter button, highlight the filters you want to clear, click the Clear Filters button, and click the Apply button. Now there are no filters. You might be familiar with the GoalSeek tool in Excel. It is used for solving one equation in one unknown. Specifically, it allows you to force a formula cell to equal a desired value by varying the value in a selected cell. For example, in a break-even model, you might want to find the sales volume required to break even, that is, to force profit to zero. At-Risk has a very similar GoalSeek tool found under the Advanced Analyses dropdown. The difference is that it allows you to force a summary measure, such as a mean, standard deviation, or percentile, of an output cell to a desired value by varying the value in a selected cell. As an example, suppose you want to find the transaction capacity in this e-commerce model that forces the mean profit to 230,000. The mean is currently about 200,000 when the capacity is set to 2 million. You can see this when I run the simulation. There's 200,000 approximately. To force mean profit to 230,000, I will select GoalSeek from the Advanced Analyses dropdown and fill in the resulting dialog box as shown here. Want to force profit, actually the mean of profit, to 230,000 by changing the capacity cell. You can speed up the search by adding lower and upper bounds on capacities to search in the Options dialog box. I'll make it 1 million and 2 million. The tighter the bounds, the quicker the search. Also, note in this dialog box that only an approximate answer is guaranteed. The mean profit will be within 1% of the desired value. The reason is that it might take too long to find a more exact value. Now I will click on Analyze. And it does a search, and the result you can see here. Your results might differ slightly because of the random numbers generated. It says to use a capacity of 1.2 million approximately. Of course, this doesn't imply that a capacity of 1.206 million will lead to a profit of $230,000. It only implies that this capacity will lead to a mean profit of approximately $230,000. Actually, if you run At-Risk again with this capacity, you will not get a mean return of exactly 230,000, but it will be reasonably close. I'll try it. Close to 230,000. In fact, if you run GoalSeek again, it is very possible that it will report a slightly different capacity, again because of randomness. Slightly different. As stated earlier, you can force any summary measure of profit to a desired value with GoalSeek. For example, with a capacity of 2 million, the standard deviation of profit is a little over 290,000. I'll show that. I will use GoalSeek to reduce this to about 200,000. Standard deviation of profit to 200,000. As you can see, the required capacity is about 1.73 million. Using that capacity, let's see what the standard deviation is. About 200,000. This video illustrates one of At-Risk's advanced tools called stress analysis. This tool is usually used to find the distribution of an uncertain quantity, given that it is either relatively small or relatively large. In technical terms, it is typically used to find the conditional distribution of an uncertain quantity, given that it is in one of the tails. Here's a typical example where stress analysis is useful. Suppose that you own an asset, such as a home, that is at risk to certain damages, such as damages from an approaching hurricane. You believe the potential uncertain damage amount is log normally distributed, with mean 200,000 and standard deviation 100,000. This implies a fairly long tail to the right, where the damage could be huge. Your actual loss is based on the damage amount. It could be the damage amount itself, but in this model, your loss is assumed to be the damage amount if the damage amount is less than 300,000, and otherwise it is the damage amount raised to the 1.1 power. This means that your loss is magnified for large damage amounts. Now, suppose you decide to purchase an insurance policy that will shield you from really large losses. Specifically, the policy stipulates that you will incur the entire loss if the damage amount is less than or equal to the 90th percentile of the damage distribution, and the insurance company will incur the entire loss otherwise. There are several questions you might ask about such an arrangement. First, what is the distribution of loss the insurance company faces? Second, what is the distribution of loss you face? And third, what amount is the insurance company likely to charge you for this policy? At-Risk's stress analysis tool can be used to answer each of these questions. I will answer the first question, how much the insurance company stands to lose, by finding the conditional distribution of the loss, given that the damage amount is greater than the 90th percentile of the damage distribution. To do this, I will set up a stress analysis from the Advanced Analyses list. I will monitor the loss in cell C6, and I will add an analysis. The reference cell is the damage cell, C3, and I want to stress high values, those above the 90th percentile. The Stress Options dialog box contains various settings. I will ask for the checked charts and place results in a new workbook. Now I will click Analyze to find the conditional distribution of the large losses the insurance company faces. The results actually show a comparison between the baseline distribution of the loss with no insurance policy and the conditional distribution of the loss faced by the insurance company. You can see this numerically in the summary sheet or in the two chart sheets. For example, the mean loss in the baseline case is about 340,000. But the conditional mean loss the insurance company faces is much greater than this, about 1.53 million. However, keep in mind that this is conditional upon the event that the damage is greater than its 90th percentile, and this occurs only 10% of the time. In other words, if the insurance company has to pay, its mean loss will be about 1.53 million. But there is a 90% chance it won't have to pay. Therefore, its mean loss overall is only 10% of 1.53 million, or 153,000. This helps to answer the third question. Specifically, the insurance company will charge at least 153,000 for the policy, and it will undoubtedly add a bit more to make a profit. Finally, to see the loss you face with such a policy, aside from the price of the policy itself, I will run another stress analysis, this time stressing low values up to the 90th percentile. Now the results compare the same baseline as before to the conditional loss you face. For example, your conditional mean loss is now about 208,000. Again, however, remember that your chance of incurring this loss is only 90%. The other 10% of the time, you incur no loss because the insurance company protects you. Therefore, your actual mean loss is only 90% of 208,000, or about 187,000. Of course, you have to add the cost of the insurance policy, at least 153,000, to this. And depending on what the insurance company actually charges you, your total mean loss could be larger than the mean loss with no insurance. That is the $340,000 from the baseline case. However, you now face less risk in the sense of really large losses, so you might welcome a slightly larger mean loss to avoid the risk.